Alright, welcome back. In this, we're going to go over one-step synthesis practice problems. I made a lifetime total of $490.38. So this video is going to be filled with practice problems that we're going to go over. My goal is to prepare you for the multi-step synthesis. So synthesis in organic chemistry is just the construction of organic molecules. Basically, you're going to be given the reactants and the products and tell me the reagents. Now, this tends to be the most difficult questions on exams, as you must apply everything you've learned from memory. Now, what is the difference between this video and the practice problems I do in my other videos when I go over a certain reaction? The biggest difference is uncertainty. I am not telling you what reactions you're going to be doing. For example, if we pull up a anti-dihydroxylation video, the one I made, and you go to the practice problems, you already know that you're going to be doing an anti-dihydroxylation. If you do oxymercuration, demercuration, and you look at those practice problems there, you already know you're going to be doing oxymercuration, demercuration. But in this video, I'm not telling you which we're going to be doing. It's uncertainty, exactly what we're going to be seeing on an exam. So what is fair game for this video? Any SN1, SN2, E1 or E2 reagents, reactions with alcohols, and all alkene reactions. I'm not going to be telling you that we're going to do all of them. We only may do some of them. And then the other ones you might see in a different video, the next video, when we do two-step synthesis. It's the uncertainty. So you may see duplicates, or you may see none at all. So that's what I'm trying to get at. Now, before we do the practice problems, I want to, go over a lesson. A very common question I keep getting is my professor makes things super difficult. It's not the reactions we've been going over. And I like to challenge that by saying, no, it is exactly what we've been going over. It's that you have to look at it from a different perspective. Let's take a look at this reaction. I plagiarized this off Reddit. We have this molecule, and then we're adding this junk, and then we're getting this. This is from organic chemistry too, but I guarantee you know how to do this reaction. Just take a look. We're doing something with tosylate, and then we have something beneath here. Well, remember, tosylates convert alcohols to great leaving groups. Well, we have a alcohol here. So that's what we're going to do. And then you would know, if you remember from my tosylate video, well, we convert tosylates to good leaving groups, and then we can do an SN2 or E2 reaction to get our desired product. In this scenario, we are doing a substitution reaction. If you don't believe me, this is directly from the video of my tosylate. We are taking an OH, we do our, our tosylate reaction here. And the second part is a nucleophile or a base. I didn't include the second part of the reaction. This is just the first part. We convert into a good leaving group, and then we can use a nucleophilic attack, do a add a nucleophile, do a substitution reaction, or add a base and do an elimination reaction. It's the exact same thing. It just looks a little more complicated. This is our nucleophile. Here's our tosylate. Here's our nucleophile. And that's what we did. I can even give another example. This is the reaction. Oh, actually, tell me what this reaction is for. Hopefully you would know it's anti-dihydroxylation. So we use a peroxy acid and hydronium. But in the challenge problems on that video, I told you that hydronium is acting as a nucleophile. This means we can use any nucleophile we want to. It does not matter. I'm just saying just to get those two OH groups, we would use hydronium. But we can use peroxy acid and some other nucleophile and get our whatever product that we need. These are just templates, if you can see. Now, the biggest thing is you need to understand what the mechanism is doing. Don't ignore the mechanism, even though you may not be asked, okay, show the arrow pushing for anti-dihydroxylation. That does not mean you should skip it. You need to understand what the mechanism is telling you. For example, yes, hydronium acts as a nucleophile, but it's also doing something else. It's deprotonating something. Well, we have our peroxy acid here. Well, we can use a different nucleophile than hydronium to get our desired product. But if we do that, we need some way to deprotonate our group, well, you should go watch the video, but what I'm talking about is we need a deprotonating agent. And that's why we use something like sulfuric acid. Even though this is not from the textbook, this is not directly from the actual mechanism or reaction from the textbook, we can manipulate all the reactions we've been learning about if you understand the concepts, the key concepts of the mechanism. So that's what I'm trying to get at. So if your professor tries to trip you up, you'll see something like this on an exam. You're like, wait a second, this looks nothing like this, what Kishan went over. No, it does. You just got to look at it from a different perspective and really understand what the mechanism is trying to tell you. The mechanism is all the mechanisms you're learning about is a story in some way. It's telling you a story. So as long as you can understand that story, which I do in all my videos, you'll understand how this is basically exactly like this. You're just getting kind of a different product. Hopefully that kind of, makes some sense to you. All right, let's do some practice here. Practice problems. Tell me the reagents you need to achieve the following transformations, or also known as synthesis. Okay, we have an alkene here, and we're adding an OH group, one OH group. We are adding the OH group on the less substituted carbon, because take a look, this is the more substituted carbon, this would be a less substituted carbon. And the reaction we learned is using BH3, THF, H2O2, and sodium hydroxide. Like that. We are only adding one OH group, not two. So this is not a dihydroxylation. This is just one. Okay. B, we have a halogen here, and then we're creating a double bond, an alkene. So this is an elimination reaction. This is the alpha carbon, this is the beta carbon, this is the beta carbon, this is the beta carbon. So in elimination reactions, we take a beta hydrogen. So it either is going to come from here, here, or here. Well, you'll notice that in the products, we're getting the one here. So the one there. This is the less substituted alkene, because if it were to go here, that'll be the more substituted alkene, because you count how many branches there are. This is the less substituted alkene. In order to do an elimination reaction and get the double bond on a less substituted alkene, you need a bulky base. And the most common bulky base is tert-butoxide. Or potassium tert-butoxide, I should say. Yep. Let's do C. Okay, we have an alkene, and then we're adding one bromine. You will notice that the bromine is on the less substituted side. So this is anti-Markovnikov. Well, whenever you only add one halogen, you use HBr or HCl or whatever you need it, whatever halogen it is, or HI. Oops, HI, right? So anything with H's, H and the halogen. Well, since we're adding to anti-Markovnikov, so the less substituted carbon, you also need a peroxide to it, ROOR, like that. This would D. Okay, we have an alkene, and we go straight to an alkane. We're not adding anything else. We're just adding hydrogens. So what do? Well, the mechanism we learned is, well, not mechanism. We didn't actually learn about the mechanism, but the reaction you learned about is molecular hydrogen with a catalyst. So H2, and then the catalyst can be platinum, palladium, or nickel. You can choose whatever you want. Does not matter. So H2 and then our catalyst to get an alkane. E. Okay, we have an alkene and we're adding one halogen. So like I said before, when you add just one halogen, this is you're already done, basically. You already know. You should make a shortcut in your brain somehow that whenever you add one halogen, it's going to be HBr, HCl, blah, 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 HI. HI. Never chlorine. Never fluorine. Yeah. Okay, we're adding this to the more substituted carbon, not the less substituted carbon, because this is more substituted than this. And we're adding it here. So it's the more substituted side. So we do not need a peroxide. We just need HCl. Okay, let's do F. We have an alkene. We are doing syn, or a syn reaction, adding an OH and an H. So what could this be? Oh, and the OH is going to the less substituted carbon. This would be more, this would be less. The OH is going on the less substituted carbon. So what do we do? Well, the reaction for the less substituted carbon addition of OH is BH3, H2O2, and sodium hydroxide. Like that. Sweet. Okay, let's do G. Okay, we have a bromine and we're adding, so it's an alkane, and we're making an alkene, getting rid of the bromine to make an alkene. This is going to be an elimination reaction. Now, there's a few reagents you could use. You need a strong base for this. And the reason we need a strong base is because look at the substitution of the alkyl halide. It's tertiary. So we need a strong base. This is being added to the more substituted carbon, not the less substituted carbon. So we do not need a bulky base. So we have a few options here. We can use sodium hydroxide, sodium methoxide, or sodium ethoxide. We can use any of them, free choice. Now, you might be wondering, why are we not doing an SN2 reaction with these reagents? You could do an SN2 reaction, but why are we not doing it? Because remember, SN2 does not work for tertiary alkyl halides. That's illegal. Only SN1 does. And these are not SN1 reagents. And you would need, so that's why. So we know this is fine to use, that we're not going to get a substitution because this is a tertiary. So this is all fine. Let's do H. Okay, we have an alkene, we're adding a bromine. Okay, there we go. So we're only adding one halogen. So that's going to be HBr, HCl, HI, and since it's a bromine, HBr. Are we adding it to the more substituted carbon or the less substituted carbon? Well, we're adding it to the more substituted carbon because we're adding it here. And this is more substituted than this side because it has more branches. So we do not need a peroxide. And this is more Kovnagov. So just HBr is fine. Challenge problem. I love this challenge problem, by the way, because it's going to teach you something very interesting. AZT, I'm not going to pronounce the actual full name of it, or whatever, thymidine. Okay, was the first drug ever, I spelled that wrong, first drug ever approved by the FDA to treat HIV/AIDS. Unfortunately, the virus developed resistance to AZT over time. Give me the reagents to synthesize compound 2 from compound 1. In addition, explain why there's a preference regarding the pi bond attack. Okay, so this is something your professor might, kind of give you. Something super big and complicated. But here's the trick. Just look at what is changing in this entire reaction. Going from 1 to 2, look what's changing. Even though this entire molecule looks gigantic, just look how many things are changing. So you'll see that this is all the same. This is all the same. Nothing here is changing. So that means don't worry about it. You could literally just erase it if you wanted to. What's changing is we're having an alkene and we're adding one OH and one hydrogen. Okay. You will also see that we're adding the OH to the less substituted carbon. We are adding it here because this would be the more substituted carbon. This would be the less substituted carbon. And this reaction, well, I should say, what reagents would you use if you're adding the OH, one OH to the less substituted carbon? You would add BH3, THF, H2O2, sodium hydroxide. Like that. And that's the answer. Now it adds syn in a syn fashion. Now, you may be wondering, this does not look syn at all. Why is this one on a wedge and this one on a dash? Shouldn't they both be on dashes or both be on wedges? So look at it very carefully. This is meant to be a trick question, by the way. Look at it very carefully. This is indeed adding syn, but to you it may not look like it. So the hydrogen is being added to a dash. That is completely fine. That's perfect. The OH looks like it's being on a wedge, but that's not the case at all. That's not what's happening. In the reaction for BH3THF H2O2 sodium hydroxide, the OH group and the hydrogen are being installed on opposite sides of the alkene. On this side and this side. Notice that the OH group is not being installed here. It's being installed here. There's a carbon right here. We cannot have two dashes on the same carbon, nor can you have two wedges on the same carbon. They must be on different carbons. So you'll see that indeed this becomes chiral. So when you do the reaction, this becomes chiral. That's a given because they're all four groups are all different. They're all different. So this becomes on a dash. It does not become on a wedge. I'll tell you why in a second, but it's on a dash. This must make this carbon on a wedge. Now, since this is not chiral, there's no reason to draw this on a dash. Yes, in reality, it would be on a dash because this is a syn addition on the same face, but we don't draw it in because this carbon right here is not chiral. Yes, this one is, this one's not. We're adding it, we're adding the hydrogen here and the OH here. There's a carbon here, so there's a carbon here, right? So we erase this carbon, this alkene, we get that, and we're adding the OH here. We are not adding the OH here. This is saying two different things. This would be saying that there was no carbon here at all and there's no alkene there. That's not what it's saying. So that's why you have to be careful. You have to be very, very careful when you do these problems. Come on. Okay, there we go. Hopefully that makes sense. Okay, now the question is why is it not, there's no enantiomer of it? Why is this one only syn addition on dashes? Why is this not on wedges? Because when we went over BH3, THF, H2O2, and sodium hydroxide, we would get enantiomers. That is, if the molecule is not symmetrical. But why? Why are we not getting the enantiomer where this is on a wedge and then this would technically be on a wedge too, but it's not because you don't depict it. The reason is because of hindrance, steric hindrance. Take a look here. The phenyl group is very big, very bulky. You'll notice that this entire group here is on a wedge. This entire group here is on a wedge. The wedge, or facing outwards to us, is so cluttered. So when this reaction happens, there's no room for the attack, for the pi bond to attack and do this whole entire reaction on the front face of it. It can only do on the back face of the alkene, because that is where, it's not sterically hindered. There's space in the back side of the, of the reaction. So that's what's happening. So if it's ever stated, or you look on a test and you realize there's no enantiomer, 99.9% of the time, it's because of steric hindrance. So if you were asked, why are we only getting this product and not the enantiomer? If you see, like, pretend on a different question on an exam, you get something very similar to this. 99% of the time, it's because of steric hindrance. There needs to be available space for the reaction to happen. So that's why it happens as a backside. It attacks the back face. Hopefully this makes sense. If you found this video helpful, please like and subscribe. Until next time, later.